So I wanted to like introduce a very important context concept in the context of rotation. So I will go for another 20 minutes or so, and then we'll stop. And the idea is that how is angular momentum exactly related to rotation? I mean, we are calling this angular momentum, but what does it have to do with rotation in quantum mechanics? In quantum mechanics, there is no particle, there is no things. What does it mean for things to rotate in quantum mechanics? Okay, so before we do that, let's take a step back and reevaluate or revisit the time evolution operator, which you are all experts now on. Okay, so somebody other than Shudosh or Nahi has to tell me what the time evolution operator is. Okay, we need some sound effects.
Tumbleweed noises.
Yeah, exactly. Okay, is it a unitary operator or a Hermitian operator?
Unitary. Oh, I wasn't supposed to say.
Yeah. Shut up, Shuyosh. Someone else? Unitary? What should the form look like? Just tell me what the form should be. Does it involve the Hamiltonian or not? Okay, clearly it's time to have a quiz. All right, so the time evolution operator is E. I'm waiting. Plus or minus in the exponential. Come on, you've got 50-50 chance of getting this right. You'll make very bad gamblers.
This is amazing.
Okay. Plus or minus? Come on.
Should I say, or should I keep my mouth shut?
Keep your mouth shut.
Okay, I'll keep my mouth shut. Thank you.
Okay. Okay, let me just remind you of the Schrodinger equation. I h bar d psi by dt, and this is h psi. So, so if I can write this like this. Okay. So does that give any clue what should be here?
It was minus IH bar something, but I completely forgot.
Minus I h bar ki upore naki niche?
Upore, in the power.
H bar something. What is that something? So
yeah, that I forgot.
Okay, it's actually minus I. That's good. It's minus I divided by h bar. Okay, and then there should be a factor of t, right? So there should be a t, and because of the Hamiltonian here, there should be a factor of h. Okay. And if you look at in dimensional analysis, you know that if these two guys will have the same dimension, whatever that is, and this will have dimension of time, so you know that ht will have the same dimension as h bar. So this is dimensionless. Okay, so always think in terms of dimensions. I mean, dimension analysis is your friend, the physicist's best friend. Okay, I'm not kidding. It is your best friend. A lot of times you can just guess answers by dimensional analysis, up to factors of 2 and pi and stuff like that. Okay, so this is the time evolution operator. Now, in group theory language, what H is doing is that H is, the Hamiltonian is generating time translations. Okay, so if I apply u of t on some state at, say, time 0, I get the state at time t. Or if I am more general, u, where the argument is t minus t0, applying on the state psi at time t0 gives me the state at time t. Okay, so in this case, the time evolution operator is going to be e to the power minus I by h bar, big H, t minus t0. Okay, right. Now suppose that we have an operator O, Hermitian. That means it is an observable. And suppose that O commutes with H, and O doesn't have any explicit time dependence. Then what is going to be this quantity, the expectation value of O? What will be the time derivative of the expectation value of O? Do you know? How can we calculate this? Suppose this guy is psi, this thing, right? So how do we calculate this from this definition?
Leibniz Rule.
Leibniz Rule, right? So, yeah, somebody, was that you, Moon, or? Okay, so as Nahi was saying, Leibniz Rule, so we are assuming that O does not depend on time. So Leibniz Rule give us, how many terms will it give us?
3.
Yeah, but one of them will not be there because O is time independent. Right, so we'll get one term like this, and another term like this, but this will be 0 because we are assuming O is time independent. And then we'll get another term which is like this, right? So now we can use Schrodinger equation. If I replace this by the Schrodinger equation, I'll get 1 over minus I h bar, the Hamiltonian acting on psi on the left, this thing, right? And from here, I'm going to get this term, I'm going to 1 over I h bar, psi O Hamiltonian acting on the right side. But there's a minus sign compared to this thing, so we can write this as I, we can take the I upstairs and H can be stay downstairs. These things don't matter. And then we have the commutator of H and O. But what did we say about the commutator of H and O? That they commute, right? So this is 0. So we see that when O is an operator which commutes with H, its expectation value does not change with time. So that observable is what we called, then O is a constant of motion. Or it's a conserved quantity. Or it is a conserved quantity. Okay. So suppose now that we have some Hamiltonian which is proportional to the total angular momentum. So then if I take our O to be J squared, then O will commute with H, right? Or even if I take, say, J, O to be, say, JZ, if that, or JX and JY, that this will be true. Right?
Yes,
Can
sir.
you guys hear me?
Yes, sir. We can hear you.
So if my Hamiltonian is of this form, just for the sake of argument, then we have this amazing result that all the angular momentum components will be conserved. That angular momentum is conserved.
Sir, is H a Hamiltonian or something else?
It's the Hamiltonian.
Oh, okay.
Okay? So, whenever we have an observable which commutes with H, whenever we have an observable which commutes with H, it gives rise to a constant of motion or a conserved quantity. Okay? So a very trivial application of this is when we take O to be H. Then we see that the expectation value of H is conserved. What do we call this statement?
Conservation of energy.
Exactly. So energy is conserved.